Hi everyone, here's another video from Math 111. This is section 1.7, inverse functions. Before we talk about functions, let's remember what functions do. Functions take inputs and produce outputs. Well, inverse functions take outputs and produce inputs. Ultimately, it's as straightforward as that. Our functions take a set of inputs and tell us what the outputs are. Inverse functions start with the outputs and then they tell us what the inputs are. So let's look at all four common representations of math and use all four to explore inverse functions. And just like with combining functions, I'm going to start with numerical. So let's start with numbers. Let's take a function that takes takes x and sends it through the function f. There's my inputs 0, 1, 2, 3, and 4. And my outputs are going to be -5, 3, 6, 8, and -7. Okay, so my function f takes x equals 0 and sends it to -5. My inverse function, the inverse of f, takes y equals -5 and sends it to 0. And that is using an inverse function. You take your output and you find the associated input. 3 going through f goes to 8. 8 going through the inverse of f is 3. Now we have notation because rather than writing words, mathematicians came up with notation. I'm not a big fan of this notation because we use it to mean something else as well. But for functions, the inverse of f of x, or more generally, the inverse of f, is written as f with the little -1 up in the power. Not great notation because we use that for something else. F inverse of y, is y was the output of f. So for a function f, the inverse is f with a little -1. And we read that f inverse. F inverse. So g would be my function, and g inverse is the inverse function. So I can take my table. Let's go back to our table. I'll write it again. F and f of x, 0, 1, 2, 3, 4 here. The inputs are on the left. The outputs are on the right, -5, 3, 6, 8, and 7. And I have all the information in this one table about my function and my inverse function. Because I could say, what's f of 2? That's 6, because the input is 2, the output is 6. I could say, what's f inverse of 7? That means the output is 7 and the input is 4. The table contains all the information I need. Let's look at f of 3. that's 8. And that means F inverse of 8 equals 3. Because this 3 is the x value associated with the y value. And so F inverse takes the y value and sends it to the x value. But what about F inverse of 3? Well, this means I need to find 3 over there in the y values, and there it is. 3 is right there, and the associated x value is 1. So the point here is you have to be careful. This particular function had 3 both as part of the inputs and as part of the outputs. But these are different 3s. The 3 on the left is an input, the 3 on the right is an output. And so you use them differently. By the way, that should make it pretty clear that the domain, the inputs for F, is the range of F inverse. The inputs of my function are the outputs. Sorry, the inputs of my function are the outputs of my inverse function. And the range of F, the outputs of F, is the domain of F inverse, the inputs of F inverse. The y values are the outputs of my function, but they're the inputs of my inverse function. This is why I like to say that tables are absolutely the easiest way to work with inverse functions, because you have all the information you need right in front of you. And all you need to do is choose whether you read the table left to right or right to left. All right, let's look at a graphical representation of a function and its inverse. So I'll draw a graph here. I have to be pretty careful this time in order to be able to use the units to my best advantage. There's my function, f of x, takes x as inputs and gives me y's as outputs. And I'll put a scale on here. So I can use a graph to ask, what is f of 1? So when the x is 1, the y is 3. I can also use the graph to say, well, what about when the y is -2? So the f inverse is -2. So I come down here to -2 on the y, and then I come over and I see that the x is -4. You've already done this. All right, you said solve f of -2. You found the x values that produce y equals -2. In a very real sense, using an inverse function is just solving for the inputs. If I know the output is -2, now I want to know what the input is. You might wonder why we do inverse functions at all. And it's because there are times when having a formula for solving, it makes things a lot faster. And so the idea of inverse functions is the same as solving, but using inverse functions, it can be helpful to have formulas. Notice also that any horizontal line will touch the graph at most one time. If I put horizontal lines and I go up, they're only going to touch the graph once. This is called the horizontal line test. And it determines if the function f has an inverse. If your function passes the horizontal line test, or if the graph passes a horizontal line test, that means that f has an inverse. So here I'll give you two examples of that. Well, one example where it passes and one where it doesn't. So here's my function f. It takes inputs and gives me outputs, x to y. And anytime I cross it with a horizontal line, it touches in at most one place. So f has an inverse. And the reason this test works is because no matter what y value you give me, I can always tell you exactly which x value it came from. Let's compare that to g of x here. And it's going to look like this. And if I take a horizontal line, I see it crosses 3 times, which means if I'm asking you what input gave me this output, you have 3 choices. You cannot be sure what the input was. And therefore, this function doesn't have an inverse. An inverse function has to have exactly one input for every single output. An inverse function has to have exactly one input to the original function f for every output of f. I find that a little easier to look at in table form. 0, 1, 2, 3. 0 sends to 1, 1 sends to 2, 2 sends to 3, 3 also sends to 2. Now this is a function because each input has exactly one output. Every time I put 1 into this function, I get 2. It's okay that putting 3 also gives me 2, but the point is each input sends to exactly one output. However, if the output is 2, the input could have been 1 or 3, so I no longer have that clear and consistent set of instructions working backwards. So f does not have an inverse function. I'm going to add in a definition. A function is called one-to-one if each input has exactly one output and vice versa. That's what it means to be a one-to-one function. Basically, in other words, a function is called one-to-one if it has an inverse function. And a function that has an inverse must be one-to-one. All right, let's move on to the symbols. Let's let f of x be x cubed minus 2. So I can use that to evaluate like f of 2, which is 2 cubed minus 2, which is 8 minus 2, which is 6. I can also solve. Let's solve f of x equals 25. And so what we would do is we'd say 25 must equal x cubed minus 2. Add 2 to both sides, and we get 27 equals x cubed. And we undo a cubic by taking the cube root. So cube root of 27 is cube root of x cubed, which is x. And if you're not familiar, you check your calculator and you find out that 3 equals x. So we started with an output y, and we found the corresponding input x. We just used the inverse function, because inverse functions are basically solving for inputs. But let's find a formula for f inverse, because, as I said earlier, formulas are a more efficient way. Now we have one formula and we can do all of this inverse. We can do all of these solving operations a lot more quickly. The process is the exact same as solving for a specific value. Here I said y is 25 and I solved for x. Set f of x equal to y and solve for x. So instead of 25 equals x cubed minus 2, I just say y equals x cubed minus 2. And then we add 2 to both sides, and we get y plus 2 equals x cubed. And then we take the cube root of both sides, and we get the cube root of y plus 2 equals x. And there's my formula for my inverse function. No matter what output you give me, I'm going to add 2 and take the cube root, and that's going to tell me the input. F inverse of y equals a cube root of y plus 2. In my mind, this is it's a lot more work than just using a table, but it's certainly something we can do when our function has an inverse. I know that x cubed minus 2 has an inverse because I know what it looks like on a graph and it passes the horizontal line test. So I can find the formula for the inverse function. And I'm always going to write my inverse functions using y as the input, because an inverse function takes you from the y values and gives you back an x value. All right, let's summarize inverse functions. You start with an output and solve for the input. This is super straightforward with tables because you have all the information. It's also very straightforward with graphs because you trace the graph backwards. It's more work with symbols because you have to solve for x. Whether you're solving it each time, like as I said, f of x equals 25, so we solve for x, or we come up with a formula using f of x equals y, and you solve that formula for x, giving you f inverse of y. The words, how I would do words as an inverse function, I actually kind of talked through it. I'm not going to write it all out. But if my function cubes x and then subtracts 2, first I'm going to have to add 2, and then I'm going to have to take the cube root. So sometimes this is called the socks and shoes method. The verbal representation of a function. You just give the instructions that undo the function. All right, so if the function is getting ready to go out the door, first I put my socks on, then I put my shoes on. If I want to undo that, first I take my shoes off, and then I take my socks off. And finally, the domain of my function is equal to the range of the inverse function, and vice versa. The range of my function is the domain of the inverse function. All right, thanks for watching.